I guess I jump into the lecture. Quick announcements about administrative stuff again. On Friday, we'll have our first quiz right here in class. And it'll be very similar to the sample quiz that I've also posted. There's no homework due this week, but please do make sure you try the sample quiz under sort of the time restrictions that you will have. I'm anticipating that it should take you at most 15 minutes per problem. So 3 problems, 45 minutes. You should be able to finish it. But we'll see how that goes. The homework grades for homework 1 are already up. Homework solutions, of course, you have for both the homeworks. I think Dr. Liu will try to get your homework 2 graded hopefully sometime tomorrow. And if you have any questions about any of the homework problems or the sample exam problems, you can come see Dr. Liu in the office hours today, 3 to 5, or tomorrow in my office hours, again, 3 to 5. Any questions on anything before I jump into the material? And as I mentioned, for the quiz, you can have a single letter size sheet. On one side only, you can write or print or do whatever, put down whatever you want. But don't stick anything. I've seen people in the past stick Post-its and try to increase the surface area. That's not going to work. So, but other than that, I think I mentioned calculators is fine. Any calculator is fine. You'll get those 3 or 4 pages of the questions, so you can write your answers on them itself. Use a pencil, it might be easier to make changes. And Frederick, you had a question?
Yeah, where's the sample quiz?
The sample quiz is posted under a section called Syllabus and Office Hours on the Blackboard main page. So make sure you try it. And of course, if you have questions, you can first post it to the discussion forum, and then of course come to our office hours. Make sense? All right, so let's jump into the material for today. I think what I'll do is I'll very quickly remind you where we were. We've been looking at this principle of real work and real energy. And using this principle, we sort of took a segue into the principle of virtual work and virtual internal energy stored in a structure. And the idea that I was telling you last time was that for such a truss problem, and that I should probably give you a hint here as well, that this is a truss problem, and on one of the questions on the sample exam is indeed a truss problem for you to use real work and real energy with. So you can follow very similar logic for that truss problem as I did here as well. So the idea was that if you apply a horizontal load P, the truss deforms from this black position to this blue position. In that deformation, the force P does some external work, some real external work. And every time we talk about real external work, we have that factor of half sitting there. Half times real force times real displacement is the external work done on the system. And in the deformed configuration, both the members of the truss act like springs. One of them is being stretched, the other one is being compressed. And when they are stretched and compressed, they store energy within them. So we calculated the energy stored real energy stored in both of those members, equated external work to internal work, and found what delta X was, which is all fine and good. Go ahead, question, Joe.
When you're looking at a full-size truss,
Yep.
for your internal energy, sum every single member.
That's right, absolutely. So if you have a truss, a big, huge truss of a bridge, say with hundreds of truss elements, and if you place a truck on that bridge, the truck is going to do some work as the bridge deforms, and it's going to store energy in each and every member of that truss element. And that's a good point, because if you remember the way that I think I tried to show you on the first page here, that's the idea that you were just talking about. If you load a truss, each and every member, all of these plots are showing the response of each and every member. So even though there are only 2 external forces that do real work, each and every member deforms and stores energy within them. So good point. Um, so that actually brought us to the question that we can find delta x with real work, real energy, but what about delta y? I cannot find delta y with real work, real energy because, of course, it's perpendicular to P. And if it's perpendicular to P, then P does not do any real work while going through that delta y displacement. So to find this delta y, we said we'll do this thought experiment. And we said that we are going to apply the real force, or this thought experiment would have two stages. In the first stage, since I want to find the vertical displacement at C, I'm going to apply a small virtual load, P prime. Everything virtual has a prime on top. Small virtual load P prime on it. I don't care what that load is or how much that load displaces the truss, as long as it is negligible in comparison to the real deflections. Okay. So once I apply this P prime, then as a second step, in the presence of P prime, I will slowly apply the real load, P. When I do that, this virtual load P prime will actually do work on the structure as it goes through this delta y displacement. Make sense? Even though the real force P does not do any work in going through the vertical displacement, the virtual load P does indeed do work in going through this delta y. And we went through the logic that that the total external work done during the process of applying this horizontal P would still be equal to or the total internal energy stored within these two truss members. And I pointed out last time that that if you were to plot the load versus deflection plot of the external forces, then the vertical force P prime that's been applied in step 1 remains constant in step 2, and therefore the work done by that P prime would be this yellow rectangle, which is basically P delta time or P prime times delta y. So that's the total virtual work done by P prime as it goes through a vertical displacement. There's no half there. There's no half because it's already reached its full value during the real load stage. On the other hand, when we do apply the real load in step 2, the real load does increase slowly from 0 to all the way to P. And in doing that, it does real work in displacing from this point and moving to the right by delta x. So the total external work done is the sum of these two areas, one big green triangle area and one big yellow rectangle, which is in turn stored as internal energy in those two truss members. So here's the internal energy stored in truss member AC, and here's the internal energy stored in truss member BC. And we have already shown using the principle of real work and real energy that this big green area is equal to the sum of these two small green areas. Therefore, this yellow area must also be equal to the sum of these two yellow areas. And that's really what the principle of virtual work is. That in the presence of some virtual force, the external virtual work done is also equal to the internal virtual energy stored. And we'll take a look at quite a few examples of this as we go forward. And last time, I think we were just about here. We said that the total external virtual work done would be P prime times delta y, this yellow rectangle. Internal energy stored would be N prime due to the virtual load multiplied by NL over AE. Can anybody remind me where does this come from? NL over AE. What is this NL over AE? That's right. It's definitely related to PL over AE. Where does that come from? What is that PL over AE or NL over AE? That's right. It's the axial deformation of member AC. This actually delta AC. So maybe I'll write that here. This entire thing is delta AC. No prime here because it's the real displacement under the real load. Okay. this is virtual force times real displacement. Similarly here, it's virtual force times this is real displacement delta BC. So no prime on the BC. And the same logic works for the external work done also. Virtual force times real displacement, this is the unknown that we are trying to calculate, is equal to the sum of virtual forces times real displacement for all the members. Okay. So I think I was going to write last time that WE, applying the principle of virtual work, which is simply that WE prime is equal to UI prime, implies that P prime times delta Y is equal to all of that. And if I cancel off this P prime on both sides, then it straight away gives me an equation to find delta Y, right? I know what the length of member AC is, length of member BC is, everything else, P is a given, is a real external load. P prime cancels off, so that's why it does not matter what value of P prime you choose, as long as it is a small value and it does not, and it's negligible in comparison to the real displacements. Make sense? So in this way, applying the virtual work and virtual internal energy principle, you are able to find a vertical displacement, even though the real force was in the horizontal direction. Okay. And of course, this number you can check with your homework 1 solutions, matches that exactly. Similarly, virtual force method can also be applied for actually the horizontal displacement, even though we could apply the real work principle here as well. But you can see that it works for horizontal forces or horizontal displacement as well, simply by calculating. In the first step, you apply P prime. Internal forces are tension of 3 over 5 P prime, compression of minus 4 5 over P prime. And then in the second stage, I'm going to, right, it's already chosen. In the second stage, I'm going to apply a real load P slowly on top of the existing P prime. Okay, and when I do that, the internal forces will build up by plus 3 over 5 P and minus 4 over 5 P. And what would be the total virtual work done? What would be the virtual work done by this P prime, the virtual force, as it goes through a real displacement delta X? P prime times delta X. Would there be a half? No half, right? Because P prime has already been applied. So for virtual work done, there would be no half there. Similarly, the internal energy stored would be just the sum of those two members. So in the member AC, the virtual force NAC prime times delta AC is what I'm doing, plus NBC prime times delta BC is what I want, which happens to be 3 over 5 P prime times the real displacement, which would be 3 over 5 P times LAC over AE of that member, plus minus 4 over 5 P prime times minus 4 over 5 P times LBC over AE. And once again, if you go through that algebra, you should be able to see that delta X also happens to be this, should turn out to be this value, which is exactly matching what we had before. So no matter which method you choose, whatever you did for homework 1, or the real work, real energy method, or the principle of virtual work, you should always get the same result, right? Any particular questions about this logic or this particular example on how this method of virtual work is working. So overall, I think the idea, hopefully you all see now, is that if you need to calculate a certain displacement or rotation, you go to that point, apply a virtual force or moment in that same direction. So if you want the horizontal direction, you apply a P prime horizontal. If you want a vertical displacement, you apply a P prime vertical at that point. That's the first step. In the second step, you apply the real load slowly. And during the second step, the external work done by the vertical or by the virtual load would be P prime times delta that you're looking for. And the same thing would correspondingly be storing internal energy, which is again internal forces times displacement, or internal moments, basically bending moments times curvature. So we'll go through some of those things as we go forward. And that will help me sort of finally outline what the idea is. This basically is what the principle of virtual work is. External virtual work is equal to internal energy stored. But the way that we'll write it is in the form that virtual external forces P prime times real external displacement, that is usually the unknown that you're trying to find, delta, is equal to sum over all the elements that we have, and nm prime times delta m prime. Oh, sorry, there's no prime. This is a real displacement. So the sum is over all the members in the truss or whatever that structure is. Okay, there's no half in this. What this also means is that if I divide through by P prime, then I should be able to write it as 1 prime, which is just basically saying a unit virtual load multiplied by real displacement delta that I'm looking for, is equal to the same summation sign, sum over all the elements of the structure, and internal force nm prime divided by P prime times displacement delta m of each member. And I think in your book they refer to this value as a small n. So I'll, just to be consistent with that, I'll mention that here. So small nm prime is the same as, when you see small nm prime in your book, that's the same as big nm prime divided by P prime in my lecture notes. In the book, I think they ask you to use a unit virtual load, which I feel sometimes confuses students, because if there's a real unit load and a virtual unit load, then you obviously don't want the magnitudes to be similar. And then finally we have the delta m here. So that in a nutshell is what the method of virtual work is. Apply a P prime, go through a real displacement, find all the internal forces due to the P prime, and multiply with real displacements. And the only unknown in such a in such an equation is this delta external displacement that you're looking for. So this is one way to find some unknown displacements. It works very well for trusses, because if you think back, there's not too many methods for calculating deflections of trusses that you've learned up until now. You might use some geometric arguments and all that, but one of the best ways to find displacements of trusses at specific points is this principle of virtual work. Although there are a few things to note about this method. One thing is that this equation is just one single equation. It allows you to find only one unknown. You have one equation, you can find only one unknown. If you want a different displacement, you need to redo the entire method by applying a virtual P prime in a different location, in a different direction, right? So if I want delta X at this point, I apply P prime at that point. If I want delta Y at that point, I need to apply P prime at that point and generate a whole new equation for that. So this method has to be repeatedly applied for whatever values you're looking for. And I think this proof I think I've repeated that proof quite a few times, but very quickly, external work done is green triangles. So if I had a truss, I had some external loads, then what happens in real life is you apply the loads and the loads do work. The truss bends and stores internal energy. So the external work done, the green triangles, the total of that is equal to the area of the real energy stored among all the truss elements. Okay. As opposed to that real process, if we do apply a virtual load P prime, then during the real displacement, it stores P prime times delta, and the same same virtual energy is also stored within each of its members. Since the green areas are equal, therefore the yellow areas have to be equal, and that's basically the derivation of the principle of virtual work. And this is something that I will insist upon again and again as we go forward. If things are not clear, you have to really stop and think deeply about it. Make sure you convince yourself that indeed WE prime is equal to UI prime, which is principle of virtual work, just because real work is WE is equal to UI. Okay. And that allows us to calculate this unknown displacement delta Y or delta X corresponding to the virtual force. Okay. Another key point here is that the principle of real work and real energy. Let me ask you this. If I had this, let's say a steel column, for instance, and if I apply a horizontal load here, and let's say that I apply a big enough load that it causes yielding of the steel column. And in yielding the steel column, I have done some work that is lost field, that's not stored in the internal energy. So of course, I cannot apply the real work and real energy principle, because whatever external work I did, partially it was stored in the deflection of the column, but partially it was lost in trying to yield the column. So yielding is not an elastic process. You know that, right? If I yield a material specimen, then I cannot, when I remove the load, it does not come back to its original position. It's not an elastic process. So real work, real energy does not work for non-linear processes like yielding. But this virtual work, virtual energy method, absolutely no problem. Works for non-linear processes also. So it's actually more general and more applicable to non-linear processes. Why is that? Because you can see here that when the yielding occurs, it definitely affects the real work and real energy. But the virtual work and virtual energy still remain that yellow rectangle. And some of those yellow rectangles would still be equal to the internal virtual energy stored in the members. So principle of virtual work is definitely more general and works better. Any particular questions on these conceptual things? Okay, so let's then try to see how it works, how this method of virtual work works for different types of structures. For general three-dimensional structures like this, we have talked about trusses and beams till now, but principle of virtual work works just fine for any structure. It doesn't matter how complicated it is. So for example, I have all this water pressure in the back of this dam. Anybody know what this dam is? Hoover Dam? Pretty huge structure if you've been there. And if you are looking for, say, a displacement at the top when the dam is filled to its full height, that's something that you can do with principle of virtual work. You can apply a P prime at the location at which you want displacement, and fill up the dam slowly. That would be the second stage. And in doing so, the virtual force P prime will do virtual work in the amount of P prime times delta. And where would the internal energy be stored? Where would the internal energy be stored as the dam fills up? Right, so this entire arch, even though it looks pretty massive and rigid, it's not rigid, it deforms. So you can think of this entire dam as a deformable body. As it deforms, it will store energy just like any other structure does, and like a spring does, like a beam does, like a truss does. Okay, but the way in which it stores energy is slightly different. It stores energy in the form of a three-dimensional stress times a three-dimensional strain, which of course we will not go through in too much detail, but just for completeness, it's the same logic. P prime times delta is equal to sum over the 9 components of stress times strain and integrate over the entire volume of the dam. That would give you the internal energy stored in the dam. So in principle, it works perfectly fine. Of course, in real life, it is difficult to find strains at each and every point. So that's how basically you would apply the principle of virtual work for a three-dimensional body like a dam. Here's an aside that's of course not in your books either, but some of you might have used principle of virtual work to find unknown forces. Have you done that before? How many of you have seen that before? Maybe long back in statics, some of you might have seen that. So the idea really is that for rigid bodies, let's say I have this rigid bar, and I'm applying this some known force here. I want to calculate the reactions. Normally, how you would go about it if you wanted to calculate reactions? Yeah, free body diagram and do sum of moments, sum of forces, calculate the unknown reactions. But the same thing, so maybe I'll back up a little. When you do that, when you draw the free body diagram and when you say sum of forces, sum of moments equal to 0, you are using Newton's laws. Right? Newton's first law, that sum of forces has to be 0 for equilibrium. As opposed to using Newton's laws, we can use energy principles. In particular, this method of virtual work. What we'll do is we'll say that if this bar was not in equilibrium, then it might not deform but displace, because we are assuming it to be rigid. It might displace in this manner. It might have a small delta 1 prime here, small delta 2 prime here. So this is a virtual displacement that we are thinking of. Real force, virtual displacement. What we just talked about was the opposite, virtual force and real displacement. So here we are talking about the other concept. In doing this displacement, the virtual work done would be F1, the real force, times delta 1 prime, the virtual displacement, plus F2, or actually this is Cy times Cy times delta 2 prime, and that should be equal to the internal energy stored. What's the internal energy stored for a rigid body? If this bar is rigid and I apply moments at the two ends, it's not going to deform, right? If it is not going to deform, then what's the internal energy stored? 0. For a rigid body does not deform, therefore we cannot store internal energy. Okay, so indeed there is no internal energy stored if the bar is rigid, and that would be 0, which immediately allows us to calculate that Cy is equal to minus F1 times delta 1 over delta 2, which you can easily verify is consistent with the Newton's laws or equilibrium. Okay, so without even using Newton's laws, without using free body diagrams and sum of forces and moments and all that, we found that Cy is equal to this. And using that, you can find all the other unknowns as well. Okay, so principle of virtual work, whether it is virtual forces or virtual displacements, is reasonably powerful. Okay. As another side note, principle of virtual displacements is not something that we are going to focus on just yet in this course. We are going to look at principle of virtual forces, basically the method of virtual work, as I showed you. But this principle of virtual work using virtual displacements is indeed used for displacement-based methods that we'll look in the later half of this course, which actually is basically something that forms the basis of the finite element method. How many of you have heard of the finite element method? Okay, some of you might actually even have used some software. It's basically a software to analyze structures and any type of solid bodies. Okay. So this method of virtual displacements forms the basis of that. But for now, we'll look at the conventional method of virtual forces is basically what we'll focus on for now. All right, so let's take a look at how or what kinds of problems we can solve with this method of virtual work. What kinds of truss problems we'll look at first, and then we'll look at beam problems. So as I mentioned, P prime times delta and all that, so I won't repeat that again. But here's sort of the methodical way in which you would solve a truss, a displacement. So in this case, for example, if I'm looking at the horizontal displacement at point C, then what would I do first? If I have this truss, I have 3 real loads applied to it, and the question says find the horizontal displacement at point C. So how should I go about it? Okay, so apply P prime at C. That's the first step. And in applying that P prime, that truss will build up internal forces in all of those members. Some members will be in tension, some other members will be in compression. Those would be all virtual internal forces, right, Frederick? At A. If you put P prime at A, you will find the horizontal displacement at A. Why is that? Because the work done by P prime would be the amount, would be equal to P prime times the distance that P prime travels, right? That's what we've been doing, P prime times delta. Even look at all of these thought experiments. We said apply P prime here. So when we apply P prime, and then in the second step we apply the horizontal load, this P prime remains there and just moves with the vertical displacement to this point. So if you're applying P prime at some point, and that point displaces a certain amount delta in the direction of P prime, that's the total external virtual work done, P prime times delta. If you apply P prime at a different location, it will do different work corresponding to the displacement at that point, right? So if you want to find displacement at C, you need to apply P prime at C. Nice.
You apply P prime in the opposite direction.
Absolutely, you can. So good point here. Even though I've drawn P prime pointing to the right, if it so happens that the real displacement of the point C under real loads is actually to the left, then the work done would be negative, right? P prime times negative delta. Yes, you can do negative work. If I have if I have a body, I apply P prime in this direction, but the displacement actually goes the other way because of some other real forces in step 2, then the work done by P prime would be negative, and it will show up in your equation, and the sign of that displacement will automatically get taken care of. You don't actually have to guess whether it will go right or left. Just apply P prime in the positive direction, to the right or to the up. Okay. So in the first step, you apply P prime, calculate all the internal forces, internal virtual forces, and in the second step, you apply the real loads, calculate the internal forces due to the real loads, And as soon as you have internal forces N due to the real loads, you can calculate the displacement of each one of those, or the deformation of each one of those members simply by NL over AE, like we just talked about a few minutes earlier. Once you have these two things, once you have the analysis for the real loads, analysis for the virtual loads, after that point, it's just algebra. P prime times delta is equal to sum of N times N prime times delta M, and cancel off P prime, and you'll find the real displacement. Okay. Here's a little idea of the types of problems that you can solve with this method. Some of these problems are actually rather difficult to solve with any other method. But as I mentioned, if there is essentially this method relies upon your ability to find the real displacement, and I should have an M here and a sub M here as well. Basically because we are summing up the internal forces times the internal displacements of all of the members of the truss. That's why this M is necessary. So this method relies upon your ability to find small or the individual displacements of each one of those members. If you can find individual displacements of each one of those members, you can find the real displacement at any other point. Okay, and here's the way it works. So if I have some real external load like this, P1, P2, P3, the real internal displacement of each member would be NL over AE. You basically find whether each member is in tension or compression, and take that force multiplied by the length of the member divided by AE is the real displacement. If an internal member is in tension N, it will extend by an amount NL over AE. It's compression, it's going to be negative, right? How about this problem? Say I have a truss and I heat up one of its members due to a fire or for whatever reason it heats up. And here's a question. I have, let's say, this truss. Let's say there are no external forces applied on the truss. Okay, is this truss determinate, first of all? Is this truss determinate? Yeah. And of course, we can see that because it's a simple truss. Simple truss is just comprised of triangles. So it's indeed a determinate truss. If I say now heat up this member EF for some reason, then will that heating up cause forces in that truss? Will that heating up cause forces in the truss? For a determinate truss, actually it won't, because this, when I heat this member up, it will just extend. And as it extends, all the rest of the truss would deform, and it would have some displacement, but there won't be any internal forces anywhere. Right? It's almost like this. If I assume this to be a truss member, if I pin this between two nodes, let's say a support here and a roller here, so it's still determinate, and then I heat this thing, it will simply expand, but it will not build up any forces, right? In order for it to build up forces, I need to have a pin here and a pin here. If I have a pin here, it becomes indeterminate. So indeterminate trusses or indeterminate structures, when we heat them or when we cause some displacement or deformation for any reason, they will develop internal forces and they will deform. But determinate trusses, when you heat them, there's no internal forces. It just rearranges itself, and that means it will have displacement but no internal forces. So here's the question. If I heat it by some amount, some temperature, let's say, and I'll write that in blue, I'm increasing the temperature by some amount T. What is the extension due to a temperature increase of T for a member like this truss member? Anybody remember from physics? Okay, yeah, great. Indeed, it is alpha, which is the coefficient of thermal expansion of the material, delta T, which actually I should have written here delta T, and times the length of that member L. So if I heat up a certain member of the truss, I can find what the displacement, the real displacement would be at some point due to that change in temperature, just by applying this principle of virtual work. Finally, there's another interesting application of this method of virtual work. Say you are out there in the field, you are bringing in tension cords and compression members, shipping them from somewhere. Something happened and one of the compression members is too short. And of course, it's not going to fit. So if you don't, you'd have to make corrections for that, of course. But if you want to find out how much it would affect having a short member somewhere or having a member that is too long, you can again use the method of virtual work, because whatever that amount of shortness or amount of amount that by which the member is too long, that can just be thought of as displacement. So you think of the truss as you had originally designed it in this manner, this blue truss, but for some reason one of those members has a delta L, could be too short or could be too long, and that delta L is nothing but the real displacement that you are applying to the truss. And in the presence of that real displacement, you can find out what the how the nodes of these truss would move. You can find out whether that small delta L is acceptable to you or not before you go in and try to construct the truss. Okay, so three different types of applications. One is a regular displacement of each member or deformation of each member due to externally applied loads. Another application is if I heat some members, there will be some real displacement, or if a member is too short or too long by a small delta L, that would also cause a real displacement. Okay, and these are the types of applications that we are going to look at. In the few minutes that I have, let's do this example. Here's a simple truss. 10 kips applied force here, 5 feet tension cords, 5 feet is the height, so angle is of course 45 degrees. And what I want is delta y at C. I want delta y at this point. Okay. So we'll do this problem in two steps. As I mentioned, we'll apply a, if I want delta y at C, what should I do? Apply P prime at C, right? If I want delta y at C, I better apply P prime at C. And I'll do that as a second step because I've written out virtual at the bottom here. I'll apply P prime here. And if I solve for all of that, let's go ahead and do that. If this is P prime, then I can actually do the method of joints and take the long route to find all the internal forces in the members. But I can also almost directly see that this particular joint is a special joint. If you remember from statics, that this P prime would be completely taken up by this member BC that would have a tension P prime. If this member is in tension P prime, those two members would be in compression, and the amount would be P prime over actually square root of 2, because we have to take into account the angle 45 degrees as well. So those would be in compression, P prime divided by square root over 2 minus P prime square root over 2. And if this guy is P prime square root over 2, this is an angle 45 degrees, then what would be the tension cord? This would be in tension by how much? Just P prime over 2 times cosine 45, right? Look at this node. If AB is P prime over 2 square root 2, Um, the horizontal component of that would be p prime square root 2 multiplied by another 1 upon square root 2. So it happens to be p prime over 2. This would be also p prime over 2. And so the more practice you do with this type of trusses, you'll be able to find internal forces much quicker. But if you don't feel comfortable with this, take the long route, do it correctly. Okay. Same thing here. That's the first step. Apply virtual p prime at point C because I want delta y at C. Second step is I need to find real displacements. I need to find real displacements of each and every member of the truss. How can I find real displacements of each and or real deformations of each and every member of the truss? And yeah, PL over AE or NL over AE. What is N there? Is the internal force in that truss member. So indeed, if I have an external load, I need to find the internal forces in each one of the truss members first to find the displacements of each one of those truss members. So if I have 10 here, what would be the force in this member? How about this joint C? What would be the force in this member BC? Zero. Zero force member, right? And if there is 10 here, it should get divided up equally in these two parts, and the vertical component of those two members has to be equal to 10, which is the same logic that we used here. So these two member forces would be compressive, so minus 10 over square root 2 minus 10 over square root 2, which happens to be minus 5 square root 2. Both of them would be in compression in the amount of 5 square root 2. If this member is in compression of 5 square root 2, then this member has to be in tension of 5 square root 2 multiplied with another cosine 45 degrees, which happens to be 1 over square root 2. So that would be just a tension of 5 and 5. And I'll let you figure that out by looking at these equations of equilibrium, which basically is the method of joints. It's not terribly complicated, I'm sure you'll see, but I think it's a good practice to try to evaluate internal forces in trusses using geometry to get quicker answers. All right, with this, I have all the information I need to apply the method of virtual work. So give me another minute and we'll finish. External virtual work done would always be P prime times delta Y. That's the one that I'm looking for. Internal force times real displacement, which I will put here. Basically, that's we just decided was real internal forces times L over AE, which is what we are going to just fill up this table for. So in looking at this truss, the internal force in member AB, maybe I'll actually have to go through here. Virtual force in AB and BD is P prime over square root 2. So I'll write that here, minus P prime over square root 2. BD is minus P prime over square root 2. AC is tension, P over 2, sorry, P prime over 2. CD is also tension, P prime over 2. And BC is tension in the amount of P prime. Right? All I'm doing is copying these forces for each one of those members up here. I'll do the same thing for real displacements now, but noting that displacement D is simply NL over AE. We'll do that with this logic. So minus 10 over square root 2, or actually minus 5 over square root 2 is the real force in those two. So minus 5 square root 2 times L of those two members is 5 square root 2 divided by AE. And the same thing for member BD. BC is 0 force, AC and CD are 5 tension, and the length is also 5. So I'll write that here. 5 times 5 is the length of the member divided by AE. and same thing here, and this last one is 0. So at this point, all you need to do is to calculate n prime times d, which is the product of this column and this column, put it here, do that for all those things, sum it up, that would be your internal energy stored, equate external work done to total internal energy stored, and you will immediately find delta Y. Okay, so let's stop here. On Friday, we'll start the quiz promptly at 1:30, so please do come on time. And we'll continue this after the quiz next week on Monday. All right, see you all on Friday.